Hi, good afternoon. My name is Mohak Chadha. I'm a third-year PhD student at the Chair of Computer Architecture and Power Systems at the Technical University of Munich, and this is my PPoPP 2023 presentation on the topic exploring the use of WebAssembly in HPC. The presentation is structured as follows. First, I will talk about the main motivation behind the work, followed by a brief introduction about WebAssembly. Then I will talk about our contributions, experimental evaluation, and future directions about how WebAssembly can be utilized within the HPC ecosystem, and finally conclude the presentation. There has been an influx of HPC-focused containerization solutions recently. Looking back at Charlie Crowd from Los Alamos National Lab in the US, Shifter from NERSC, Singularity from Berkeley National Lab, Bodman currently maintained by Red Hat, Ceres from the Swiss National Supercomputing Center, and last but not least Docker, which is not entirely suited for HPC environments, but in some ways part of the ecosystem, especially for building OCI compliant container images. Going back to the basics a bit, so what are containers? Containers are essentially processes. They use specific Linux primitives such as C groups and particular Linux namespaces such as mount and user in most cases to give a process a different view of the kernel resources. They share the underlying Linux kernel and can be executed on multiple platforms. They also offer flexible isolation, for example, setting system call filtering profiles using seccomp eBPF. So why do containers make sense in HPC? Containers allow developers to define custom software stacks for their scientific applications and not only rely on specific modules which are present on the HPC system. In addition, they allow developers to create reliable and verifiable environments that can be reproduced in the future. Despite their increasing popularity, the adoption and usage of containers in HPC systems is still significantly limited. According to workload data from NERSC, only 8% of the total jobs actually use containers. Let's look at some of the challenges in container-based HPC application development. So one of the biggest challenges is that for executing containers, most containerization solutions require root privileges, which are not possible for HPC systems due to shared file systems. There are also solutions such as Singularity and Podman, which support rootless containers, but their current implementations have some drawbacks. For example, they do not support parallel file systems commonly found on HPC systems. Also, building OCI compliant application container images almost always requires root privileges. So you cannot really do that on an HPC system. So now let's look at the most common workflow for building scientific application container images. You have your own laptop and workstation where you build the container image, test it, and then run it on the HPC system. However, this scenario has a lot of problems. First, HPC systems are becoming more heterogeneous with different processor architectures. Since performance is really critical in HPC, what you want to do is compile the application using the specific microarchitectural features of a particular processor. So in most cases, this laptop or workstation is x86-64, and then you want to cross-compile and build the application container for an ARM system. While there are plugins which allow, such as BuildX, which from Docker, which allow you to do this, it is significantly time-consuming. Moreover, testing and developing HPC applications offers insights only on the target system where the application will eventually run. Additionally, most scientific application container images range from several megabytes to gigabytes, and frequent network transfers from your laptop to the HPC system can be quite cumbersome. Also, most applications require special networking libraries or compiler licenses, such as ICC, which are only present on the HPC system. Finally, while there is a lot of literature out there which highlights that different containerization solutions have almost no impact on the performance of the containerized application, building a high-performance scientific application container image is non-trivial and requires a lot of knowledge about the target system and the networking libraries. So what if there was an alternative that could address all these problems? This is a tweet from Solomon Hykes, who was the founder and CTO of Docker, and essentially says that if WebAssembly had existed in 2008, when Docker was created, there would have been no need for Docker. So what is WebAssembly? WebAssembly originated as an alternative to JavaScript in web browsers for executing code with high performance. Essentially, it is an universal intermediate binary instruction format. It also offers an alternative human readable text representation called WebAssembly text format, or WAT. It has a set of instructions that are defined in the WebAssembly specification and is meant for sandbox execution in a virtual machine. It has a 32-bit linear memory address space, so the maximum memory possible for a WebAssembly application currently is 4 gigabytes. This memory is separated from the host memory address space. Unlike containers, WebAssembly provides lightweight isolation at the application level based on software fault isolation and control flow integrity. It is important to note that everything is unprivileged and occurs in user space in WebAssembly. So when an application is compiled to WebAssembly, it is called a module. The Wasm module contains function definitions, declaration of global variables, and tables for storing function references. On the right, you see a WebAssembly module for a C application that adds 2 integers in WAT. All Wasm modules are executed by a WebAssembly embedder or runtime. These Wasm modules are portable across processor architectures and operating systems. Essentially, you can run them anywhere. So a simple way to understand this is that modules are Wasm equivalent for binary formats like ELF, Marco, or PE on Windows. WebAssembly defines an import-export system for granting different capabilities to the module. By default, a WebAssembly module cannot interact with the host system or perform I/O operations of any kind. Any system interactions that is to be initiated by the WebAssembly module must be done through the functions imported from the embedder. So on the right, you can also see that the module exports its memory and the start function, which can be utilized by the embedder to execute the module and write to the module's linear memory. So what is an embedder? It is essentially a program that executes the WebAssembly module. In addition, it provides an isolated execution environment for executing the module on any platform. Furthermore, it is responsible for compiling the WebAssembly module to native machine code through several strategies such as just-in-time compilation at the time of execution or ahead-of-time compilation. It also provides definitions for all imports of the Wasm module. The embedder is not portable and needs to be built for that particular target platform. The embedder can also link against native libraries which are present on the system. Additionally, the embedder provides the ability for executing a Wasm module on any POSIX environment. This is done through WASI, which is the WebAssembly System Interface Specification, that needs to be implemented by an embedder for executing any POSIX compliant Wasm module. So in this paper, we propose using WebAssembly as a distribution format for packaging MPI-based HPC applications. So the main idea is that an HPC application can be compiled to WebAssembly once and executed on any platform by a supporting WebAssembly embedder. Towards this, we implement a tool to simplify the compilation process and implement and present MPI Wasm, an embedder for high-performance execution of MPI-based Wasm modules. We currently support C++ based MPI applications. we implement a custom header file that can be seen on the left that provides definitions for different MPI data types such as MPI-OP and the signatures for different MPI functions. We integrate this into the WebAssembly System Interface SDK, which combines the Clang compiler and the VASI libc library for compiling POSIX-based C++ applications to WebAssembly. Second, to automate the compilation process, for example, downloading the different dependencies for your system, we implement a custom Python-based tool that does that for you. On the right is again a VART representation for an MPI-based C application. You see here that everything is an integer. This is because we abstract all data types as integers from the perspective of the WebAssembly module, which are translated to native types at runtime by MPI Wasm. As a result, all WebAssembly modules for MPI applications are portable across different MPI libraries. So MPI Wasm is a WebAssembly embedder which extends Wasmer, another popular embedder. We support MPI applications conforming to the MPI 2.2 standard, and to facilitate the adoption and suitability of MPI Wasm in HPC environments, it enables the high-performance execution of MPI-based Wasm modules, has low overhead for MPI calls through zero-copy memory operations. This we accomplish by automatically translating from the linear address space of the WebAssembly module to the host memory address space. In addition, MPI Wasm offers immediate support for high-performance network interconnects such as Intel OmniPath, which are commonly found on HPC systems. So MPI Wasm incorporates an ahead-of-time compilation strategy for translating WebAssembly instructions to native machine code. For this, we use the LLVM compiler infrastructure, where the WebAssembly instructions are translated first to LLVM IR and then to the native instructions. To offset larger compilation times, we also implement a caching mechanism in MPI Wasm, which prevents recompilation overhead of MPI-based Wasm modules before each execution. So how does the memory address translation work? Imagine you have an MPI application. The MPI API is based on the library being able to read and write directly to the memory of the application. However, the executing WebAssembly module can only provide memory addresses in its own linear memory address space, while the target MPI library requires addresses in the host memory address space. So when you execute an MPI module in MPI Wasm, it reserves a part of its own memory address space for use by the WebAssembly module. In addition, it records the base address of the WebAssembly module. Using these, it is possible to directly convert 32-bit pointers that refer to the module's linear address space to 64-bit pointers that refer to the MPI Wasm's address space, and vice versa. So for implementing MPI function in MPI Wasm, we combine memory address translation and data type translation. For directly utilizing the host MPI library, we use the project RSMPI, which provides MPI bindings for Rust. So when a WebAssembly module calls a particular MPI function with a specific linear memory address space, this address is translated to a 64-bit address expected by the host MPI library. After the successful invocation of the function, the status pointer is translated back to the 32-bit, referring to the Wasm module's linear address space. Moving on to experimental results. For our experiments, we used two systems. An HPC system based on the Intel Skylake processor. For this, we use up to 128 nodes. We also use one node of AWS Graviton 2 processor based on the ARM Neoverse architecture. For our experiments, we use standardized benchmarks such as the Intel MPI benchmark, HPCG, IOR, IS, and DT. So first, we take a look at what is the binary size when you compile an MPI application to WebAssembly. Compared to dynamically linked binaries, we observed that WebAssembly binaries are smaller for two applications. As compared to static binaries, WebAssembly binaries are almost 140 times smaller. As compared to containers, WebAssembly binaries are still significantly smaller. In the presentation, I only show results for some experiments, but the rest can be found in the paper. Error bars in the graph represent minimum and maximum values for the iteration timings. For the Intel MPI benchmark ping-pong, we observe 0.05x average GM slowdown on our HPC system across all message sizes. For send-receive, we observe a 0.06x average GM slowdown across all message sizes. For the Graviton2 processor, we observe similar performance for ping-pong, while for send-receive, we observe a 0.07x average GM slowdown across all message sizes. For HPCG, we observe similar performance up to 192 MPI processes. On increasing the number of processes, we observe a performance drop with MPI Wasm. This is because of the repeated data type translation overhead due to frequent communication in HPCG. We also characterized that in the paper. So 14% was actually the maximum overhead we observed for any application. So what does the future hold? The WebAssembly community has proposed several extensions to the WebAssembly specification that can be implemented in an embedder to improve performance. I would like to highlight a few of them here. First is the extension to the WebAssembly SIMD specification. WebAssembly currently supports only 128-bit SIMD instructions, while modern processors support 512-bit SIMD instructions or even higher with scalable vector extensions. Essentially, the WebAssembly flexible vector proposal aims to provide support for instructions that are wider than 128-bit. To demonstrate this effect, consider the execution of the DT benchmark, which benefits greatly from vectorization. For this, we observed 1.36x better throughput for WebAssembly with SIMD as compared to Wasm without SIMD. The WebAssembly threads proposal lays the foundation for WebAssembly modules to define shared memories. Implementing APIs such as OpenMP in an embedder can enable the execution of multi-threaded WebAssembly modules. Partition global address space is a programming model for parallel distributed memory applications that introduces a memory address space that spans the local memory of multiple processes. Implementation of the Wasm multi-memory proposal that allows a WebAssembly module to define or import more than one memory can enable this use case. To conclude, using WebAssembly in HPC is an exciting research direction, and it has the ability to provide competitive performance in the HPC domain. In HPC, WebAssembly offers various advantages, such as portability across CPU architectures and operating systems, and a capability-based security model, which allows users to define exactly what functions a Wasm module has access to. Thank you.